Hi, this is Nick Pizzi, and this is a video in our practical math series for water treatment plant operators. I'm going to share this with you. And today we're doing something a little different. We're doing practical math for ion exchange process. Let's launch into that. So this is the ion exchange math for water treatment plant operators. It's a traditional math approach that used to be encountered by operators of hardness removal ion exchange water treatment plants back in the days. Nowadays, they invent or engineer a lot of exchange materials for specific issues, but in the old days, it was just a matter of exchanging sodium for calcium and magnesium, therefore removing the hardness of the water, typically of well water. These were a lot of small water treatment plants, many of which are still in existence. So we need to preserve this practical math. So we put this module together and we're going to launch into that now. As with all of our practical math series, you see the standard units and US conversion factors that we add that you can refer to while you're doing some of these math problems. There's going to be 10 questions on this exam, so you will be referring back to the table on and off. We have our table for formulas and values, some constants and properties. Notice that I have 3 columns in gray here. This is for the existing water treatment plant we're going to use for our exam today. And I've listed some of the design and operational criteria that you can use. I'm going to go through some schematics so that it'll make a little bit more sense to you, but you'll refer to this table to get information. For example, you can see that there are 5 well pumps. There's a hard water clear well. There's iron removal filters. They give you some information about the raw water and finished water hardness. They tell you that the plant is operating at 1,200 gallons per minute. So there's various amounts of information here that you can refer to help you with your exam problems. But let's look at the schematics. And in order to fit this on this format, I've had to split the schematic in half. And so let me start out by saying that, again, this is a traditional hardness removal plant. We're using well water, and the well water has iron in it. And in the traditional plants, we had to remove the iron first because you did not want to add raw well water with iron in it straight to the ion exchangers. Otherwise, you would foul the material and it would be unusable after a while. So the designers of these facilities found it useful to create a layout of 2 water treatment plants in series. The first plant would be the iron removal portion, where they would oxidize the iron in some fashion, filter the water to remove the iron. We go to a clear well of very hard but very clear water, and that clear water that would then be pumped through ion exchangers to remove the hardness material. So we have to look at 2 different diagrams. I'm going to show you the first diagram, which is the top half of the plant, the first part in series, the well system. And then after that, I'll show you the second schematic, which is the hardness removal system. But here's the well water system. You can see that upper left-hand corner, we got 5 well pumps. These wells pump water up and onto a coke tray aerator. These were just trays out in the atmosphere that had coke, chunks of coke, which is just a coal that provides an inert material for the water to splash down and over, thereby reducing the water into a large amount of surface area for a small amount of water. And so you get a lot of good exchange between the oxygen in the air and the water itself. So it's just a cheap way of taking oxygen out of the air and allowing it to oxidize the iron. The bad news is once you did that, you lost the pressure on the water that you just pumped out of the wells. So you're going to have to pressurize it and pump it a second time. So the good part about these was that it was free air. The bad part was that you had to pump the water twice. Anyway, after the water went through the coke tray aerator, went into the reaction basin that provided some detention time for you to oxidize the iron out of the water and let it settle out. So periodically you would have to take residue, and you'd have to draw off the residue at the bottom of the reaction basin and send that iron waste to a lagoon, as you can see there. And there are several discharge points into that lagoon, and I'll cover all of them. And then when you did that, the water would move out of the other end of the basin down by gravity to the filters. These are just standard gravity iron removal filters, just sand filters. They list that there are 3 there, and they're 10 feet by 16 feet. You notice that the water then goes down through a 16-inch pipe into the bottom portion there is the clear well itself. That was a hard water clear well. It was free of iron at this point, but it had hardness in it still. You took some of that water off and pumped it to backwash the filters when necessary. And that spent filter backwash water would go over to the lagoon also. So we're going to do this in 2 exams. The second exam is going to have a lot to do with that lagoon and the waste materials that we produce, but this is mostly about treating the water for iron and treating the water for hardness. So These filters, of course, are backwash, as I mentioned. Backwash water goes to the lagoon, and that hard but clear water then is ready to be processed for the hardness exchanger. So we're going to go to the second diagram, which is brings the bottom of the hardware clear well up to the top of the next diagram, and you'll see where we go from there. Again, at the top is our hard water clear well. I give you some dimensions of it so you can figure out how much water is actually in it. And you see that there are 4 high service pumps there, and they list the gallons per minute rating of each. That takes that water, that hard clear well water, from the well and sends it through the softeners. And you notice that some of that is bypassing around the softeners. And the reason behind that was that ion exchangers will reduce the hardness to 0. And it's not a good idea to put 0 hardness water into your distribution system. You have very unstable water and eat up the pipes. So traditionally you would pump or bypass some of the water around the softeners and reblend it after it was softened to 0. So you would take hard water, blending it with the soft water. If you did it in the correct proportion, you had a way of making the desired amount of hardness in your finished water. And so you see they provided you with a softener meter there in the middle of the drawing there so that you could determine how many gallons per minute you needed to get around a softener. And that was determined by knowing the desired amount of hardness in the water, and you would take the finished water hardness divided by the raw water hardness, and you get what we called a percent bypass. And that percent bypass was what you had to use to determine the amount of water that did not get softened. The water then goes through the softeners and is put in. We put in some fluoride, we put in some chlorine, send it out to the distribution system. Now, when you ran these softeners, they would run until they would no longer soften the water. They would go to 0, or they would go to exhaustion after producing all this 0 hardness water. At that point, you had to take it out of service and regenerate it. Regenerated to soften the resin in the exchanger by running brine water into the softener and let it soak for a while, so that you would then replenish the sodium that you had previously exchanged for the iron, the calcium, and magnesium. So when you got enough sodium back into the resin, you backwashed it with clear water, and that was also sent to the lagoon. So that makes a third stream going to the lagoon, and then you would put that unit back into service. We mentioned that we pumped that clear hard water from the well to this through the exchanger. So in other words, this was the second chance we had to pump the water and repressurize it. We pumped right through the softeners right out to the public. So you had to be good at what you were doing. Once you pumped it, there's no chance of regathering it and recreating it again. It's going right through those softeners, and you better know what you're doing at that particular point. Otherwise, you're going to have a problem. Again, when the unit became exhausted, it had to be regenerated using the brine solution. The operators would typically have a large tank in which they would put rock salt, clean rock salt, and fill it up with water, and they'd stir it up. And as long as they could still see rock salt on the bottom of the brine tank, they knew they had saturated brine, because there will come a point at 25% where the water will no longer dissolve any more salt. So they have concentrated brine. It's always 25%, as long as you have some excess salt in the bottom of the unit. Okay, so let's move on to our questions. Let's have a little bit of a discussion here on each unit as we go. We'll start with question number 1. And remember that if you want to do the math on these problems, go ahead and pause the video, and then you can work it out with pencil and paper and a calculator, and then restart the video. Otherwise, I'm going to work right through these. But question number 1 is a rather simple one. It simply says, express the hardness of the well water supply and the water leaving the exchange units in milligrams per liter. Remember, they gave it to us in grains per gallon. They want us to convert it to milligrams per liter. So when I go into the material that we presented, we go into one of the tables, we see that there's an equation that says that 1 grain per gallon of hardness equals 17.1 milligrams per liter. Grain per gallon was just a convention they used a lot in the old days, because when you had that much hardness, it was more convenient to express it in grains. Otherwise, you get huge numbers, and you'll see why later. So we have 1 grain per gallon equals 17.1 milligrams per liter. I just needed to go in and find the well water hardness off the diagram, which listed it as 20 grains per gallon. If I multiply the 20 times the 17.1, I get a raw water hardness of 342 milligrams per liter. Now, the second part of that question is, what is the water hardness leaving the exchange units in milligrams per liter? Well, leaving the exchange units, it better be 0, otherwise you got a problem. That's a trick question. It always ends up on the exams. Don't get fooled by it when they ask you that. The water leaving the exchanger is 0 hardness. All right, let's move on to question number 2. Question number 2 says that at the current flow rate, What is the detention time in hours in the reaction basin? Obviously, we want some detention time in that basin because we've got the air that has become in intimate contact with the water. We want it to do its job. It's not something that happens very quickly. So we want an hour or two of detention time for that to go to work and allow those particles of iron, oxidized iron, to settle. So I'm going to remember that the detention time form is always the volume divided by the flow rate. So we're going to take the volume of the water in the basin divided by the rate of the water flowing through it. And from that table, we find that the current flow rate is 1,200 gallons per minute. So from the table, we see that the dimensions of the reaction basin were 60 feet by 30 feet by a 10-foot water depth. If I multiply those together, multiply by 7.48, I get the gallons. I can divide that gallons by 1,200 gallons per minute, change the minutes to hours by multiplying by 60, and I come up with an answer of 1.87 hours, assuming my math is correct. I hope yours was too, and that you got that right. And we'll move on to question number 3. And again, remember, if you want to work these out, read the question, pause the video, and move on. Okay, here's question number 3. What's the total head and feet on the well pumps? This should be relatively simple. The head, as I see it, would be the difference between the water table, which is below the ground level, the pumps pump from, and the discharge point at the top of the coke tray aerator. So if I find those two dimensions on one of the drawings, which I find in the first drawing, I see that the head would be the difference between 1,035 feet and 932 feet, or about 103 feet of pumping head. Okay, question number 4. What's the filtration rate at the current plant flow? Now, in order to do this, you had to dig out that current plant flow. You also had to see from the information that they gave you in the tables and the diagrams, the filters were 10 feet by 16, and they ran all 3 of them at one time. You had to know that. You couldn't say, well, they were only running 2 or only 1. No, they were running all 3. When the plant operates, all 3 filters are online. When I take the filtration rate, I'm going to take the 1,200 gallons per minute and divide it by the fact that 3 filters are online. They are each 10 by 16. So it's 1,200 gallons per minute divided by 3, divided by 10, divided by 16. And I come up with a filtration rate of 2.5 gallons per minute per square foot. Hope you did well on that. Let's move to question number 5. We're almost halfway through. If one filter is backwashed at the rate of 15 gallons per minute per square foot, how much water would you use in a 12-minute backwash? Again, that's pretty simple. Again, you need to know the dimensions of the filters. So 15 gallons per minute per square foot, and there are 160 square foot in a filter because they're 10 by 16. And you're going to run that for 12 minutes. I come up with 28,800 gallons for each backwash. Okay, question number 6. What is the capacity of the hard water clear well? And how long will it take to drop the well 8 feet if the wells are shut down, but high service pumps number 1 and number 2 continue to operate? So there's a couple things they're asking you for here. What's the capacity of the hard water clear well? I'm going to figure all that out. Then they're asking you, if I shut the well pumps off, but I'm still taking water out of the other end of the clear well by running it through the exchangers, how long can I do that if I drop it 8 feet? Okay, so 2 parts of that question. So the clear well capacity is pretty straightforward. I'm going into the diagrams and I see that the clear well is labeled at 100 feet by 15 feet by 40 feet. I convert that to gallons by multiplying by 7.48. And I come up with a value of 448,800 gallons. Now, from the diagram, I see that the high service pumps number 1 and number 2 are each 1,400 gallons per minute. So they're implying that the flow rate is 2,800 gallons per minute. So now I need to figure out what 8 feet of water in that clear well amounts to. So an 8-foot drop would be 100 feet by 40 feet by 8 feet by 7.48 gallons per cubic foot divided by the flow rate converted to minutes per hour. And I come up with a drop time of 1.42 hours. Hope you're doing well. Let's move on to question number 7. Only 3 more to go. What's the hardness removal capacity of the 3 softeners expressed as grains? And now we're getting into the heart of some of these questions. Typically, this is the biggest job that the operator would have to do on shift at the water treatment plant for ion exchanges. You gotta know how long they can run their softeners. And this is the first part of figuring that out. What's the capacity to remove material before you run to exhaustion? Here's what I did. I looked at the diagram and I showed that there are 3 units. and each of them are 12 feet in diameter and a 3-foot depth. So if I have 3 units and I multiply them by pi times the radius squared times the 3-foot depth, I come up with a total amount of exchange material equal to 1,017.36 cubic feet of material. Well, now I got to figure out what the capacity is of each of those cubic feet. If I look at the diagram again, I see that the exchange material is rated at 24,000 grains per cubic foot. I think they probably make resin today that's a little bit more powerful than that, but back in the day, 24,000 grains per cubic foot was pretty good. So each cubic foot of material I have will remove 24,000 grains before I go to exhaustion. So if I multiply that times the total amount of material that I have, I should get the exhaustion point. If I take the 1,017.36 cubic feet, multiply it by the 24,000 grains per cubic foot, and I come up with a removal capacity of this water treatment plant of over 24 million grains of hardness. That's how much hardness I can remove. So if I know how many grains of hardness coming in, I'll be able to figure out how long I can run this plant before I go to exhaustion in this question. So let's take a look at it. Question number 8 says, at the current flow rate, what is the bypass in gallon per minute, percent bypass in gallon per minute, and how long will the units reduce the hardness to 0 before needing regeneration? And note that I put something on the bottom there that's pretty important. Since all units have to be regenerated every 24 hours, the operators typically would stagger these units so that one per shift would come open and available. And that is what was important to these operators of these traditional ion exchange plants. When you came and worked your 8-hour shift, your biggest job was going to be to realize that you were going to regenerate an ion exchanger. You had to know when it was going to come due, because you had to do some other things to prepare for that. You had to be able to run that softener almost to exhaustion, take it out of service, and regenerate it. You had to know how to figure out when that was going to be. Is it going to be 6 o'clock tonight? Is it going to be 10 o'clock tonight? I got to figure that out. So here's how they went about it. First, they would calculate the percent bypass. And we mentioned before that the percent bypass would be the finished hardness divided by the raw hardness, or 7 grains per gallon divided by 12 grains per gallon. You come up with a 0.35, which is 35%. So that means that 35% of the water is being bypassed. So to calculate the gallon per minute bypass, I would take the 1,200 gallon per minute that the plant was operating at, multiply it by 0.35, and I come up with a 420 gallon per minute bypass. So of the 1,200 gallon per minute that this plant is operating at, 420 gallon per minute of it does not go through the softeners. It bypasses and is later on blended back in with the other water that's going through there. So this water with 20 grains per gallon hardness, 35% of it is coming around the softeners. The 65% of it with 20 grains per gallon hardness coming through. We blend them together, we ended up with the 7 grains per gallon hardness. Obviously, the more water I'm willing to bypass, the longer I can run my plant before I go to exhaustion. They were willing to run it such that they ended up with 7 grains per gallon. Now, how long did that take? So they find the total hardness removed, which we went into question number 7 and got that. I'm going to find out the time it takes to do that. So in 7, we figured out that over 24 million grains was removed at a rate of 1 gallon or 20 grains every 1 gallon. So every gallon that goes through that softener is stripping away 20 grains of removal capacity. Well, I've got over 24 million grains of capacity. I'm removing 20 grains each time. I'm going to convert that and come out with an exhaustion rate of about 26 hours or a little over a day. And now that makes sense. So if you have 3 softeners and they run for over 24 hours, it's a simple matter of the operators exchanging or by staggering these so that one came due every 8 hours. And that's how they ran their treatment. Makes sense. Okay, question number 9. How many pounds of salt are needed to regenerate a softener? Okay, so now we're into that phase where we've exhausted our softener, our exchanger. I'm going to take it out of service, put brine into it, backwash it, and fix it up so that they're ready to go for another cycle. So from the drawing, we see that the amount of salt needed is 12 pounds per cubic foot of exchanged material. Well, the total cubic feet of exchanged material was found out by taking 3.14 times 6 times 6 times 3, or 339.12 cubic feet. Notice they didn't ask you for all 3. They're telling you you're going to do one at a time. Total cubic foot of one softener is 339.12 cubic feet. So for that 339 feet, I can multiply by the 12 pounds needed per cubic foot. It turns out I would need about 4,069.44 pounds of salt to regenerate a softener. So moving on to the last question, number 10, if it takes that much salt, they're going to ask us how many gallons of brine is going to give you that much salt to regenerate this softener. So in the question number 9, we calculated that we would need 4,069.44 pounds of salt for the unit. Now, salt is found in the brine that we have on hand, and it has a specific gravity of 1.19. So if I multiply the 1.19 times 8.34, I would get a pounds per gallon brine solution of 9.92 pounds. However, that 9.92 pounds is not all salt. Only 25% of it is, because that's the strength. Remember, saturated brine is 25%. If I take 25% of the 9.92, I get 2.48 pounds per gallon of brine. So now I can take the 4,069 pounds that I needed, multiply it by 1 gallon over 2.48 pounds. I'm going to need about 1,640.9 gallons of brine to do the job. All right, I hope you did well on that. That's the end of our exam. We're going to make a second one on this same data. We'll look for that in a few days, few weeks maybe. Hope we found some value in this one. Remember that operators of this type of facility have some very unique challenges in their job keeping the water treatment plant up and running. So tune back. You'll see some icons scrolling up. You can access more videos, practical math videos and others by clicking on these icons. Hopefully you find these interesting. And for now, I'm going to close out and say thank you.